Hello everyone, my name is Vrinda Krishnakumar. I am a PhD student in the Geomatic Division of the Research Institute CTTC in Barcelona. My work has been focused on developing tools to exploit the wide area coverage, the high coherence, and temporal sampling provided by the Sentinel 1 satellites to allow mid and long term monitoring of the deformations. The proposed methodologies are applied for the semi automatic identification and pre screening of the deformation processes in different areas. In this poster, I would like to show three case studies in areas with different characteristics. The first approach, called the direct integration, is a fast and unsupervised approach to map and monitor active areas in remote and natural environments. This procedure provides a rapid and simple solution to screen wide areas and to map the evolution of relatively fast and local movements. The direct integration approach uses a set of n-1 interferograms as the input data calculated by using n consecutive images. These interferograms undergo pixel selection and phase unwrapping, and the phases are directly integrated to calculate the accumulated phase over time for each point. Then followed by atmospheric phase screen estimation and filtering. The remaining phases are transformed to displacement and geocoded. The figures shows an interesting area affected by displacement with a corresponding deformation time series. These deformations are related to slope instability along the open pit resulting from excavation and the mining exploitation. This method does not have an equality estimator. It is worth noting that despite these potential errors, the target of the analysis is fulfilled since it provides enough information to detect active areas. When the direct integration was carried out in El Hierro, a variant systematic signal which shows no characteristics of noise among the multi-looked interferograms mimicking deformation signal patterns were shown in some areas. This signal is named fading signals because of the reason that the signal perishes with the increment in temporal baseline. Since the ground validation of these signals were difficult to be undertaken and the area is of highly complex physical phenomena, it was practically easier to adopt new methods. Keeping in mind that the main goal of all interferometric analysis is to discover deformation time series of the active areas from the interferograms fast and correctly, the next procedure called splitting was developed. According to INSAR principle and frequency spectrum analysis, the interferometric phases can be divided into two parts, high frequency and low frequency. The approach proposed here is to split the consecutive wrapped interferograms into low and high frequencies. The noise and the deformation phase is retained as high frequency segments and the atmosphere as the low frequency segments. An empirical threshold frequency is used in the Butterworth filter to separate. Heavy surface loads can be recognized in the Barcelona airport and the port, whose subsidence has already been more than 10 centimeters from January 2017 to 2019. Even though this approach helped with the detection of active deformation areas, the presence of the fading signals again in these multi-looked interferograms might affect the accuracy of the deformation calculation. Hence arose the need for a new method which is practical and can omit these kinds of points showing fading signals. This method is called the PSIG short temporal baseline approach. It was a slightly different PSIG approach by constraining the temporal baselines to a given threshold. The main objective of the chain is to extend the interferometric analysis to wider areas using a unique, redundant, and connected network of points. The problematic fading signals has been corrected in majority of the points using this approach. It also has the same advantages of the previous approaches, that is easy to implement and also providing robust results.